This video will focus on the learning target. I can determine the overall polarity of the molecule. So bond polarity is determined by electronegativity difference, but molecular polarity is more complicated. The problem is when it comes to a molecule, we need the overall molecule to have an unequal distribution of electrons or a pooling of electrons. And that doesn't just happen because of bond polarity, because our molecules have geometry. They are three-dimensional objects. So if we look at what I have on the screen here, I have three different molecules. And for each one, I have looked at the electronegativity difference and recorded it down. So we can run through these three molecules and decide just by looking at them whether their bonds are polar or not. Right? O and H, 1.22, totally polar. Carbon oxygen, 0.89, totally polar. Carbon hydrogen, 0.32, it's right around that non-polar, right? I'm 0.3, not yet at 0.4. So most of my bonds on here are polar, with one bond being non-polar. There's additional nomenclature on here right now, which are these weird arrows that have like a plus or like a cross on the end of them. So these arrows right here are called dipole moment arrows. Okay, so dipole moment arrows. And a dipole moment arrow is a vector. Some of you have heard about vectors in math before. And a vector essentially is an arrow that indicates the direction and magnitude of whatever your measurement is. So my dipole moment arrow is pointing in the direction the electrons are being pulled. So it's always pointing toward my more electronegative atom because it's showing me where it's pulled. And then the length of it is representing the strength of that pull. Now in the end, we won't get really specific like math is about our vectors, but if you understand a vector, this might help you. Okay, so in water, I have a pull happening toward oxygen, right? And that is a polar bond. But the question then is water overall polar? Do I have an area where electrons are being pulled in one direction? So if we look at water right now, and I looked at the dipole moment arrows, what we see is they're both pointing toward oxygen. And up here on oxygen, I also have all these electrons. So the oxygen is pulling the electrons up here, and I have extra lone pairs. So this is definitely an overall polar molecule. I have this area of negativity up here where all the electrons are pooling, and an area of positivity down here where they're vacated, right? There aren't any electrons. Now, you can also figure this out by using your vector rules if you know anything about vectors. We can take one vector and add it to the other vector, and if I end up with a resultant, that means I have polarity. I have an overall pull. You compare that then to carbon dioxide as an example. Carbon dioxide has completely polar bonds, right? Carbon oxygen, electronegativity difference of 0.89, that's polar. But in terms of, is there an area of polarity on this overall molecule? The answer is no. And that's because oxygen's pulling this way and oxygen's pulling that way. And I often think of this as a tug of war, in that if oxygen's pulling this way at the same strength that the other oxygen's pulling that way, nobody wins. And if nobody is winning the electrons, it's nonpolar. If you think about them as vectors, essentially we're pulling this way, add it to this, pull that way, there's no resultant, everything's canceled. This is a nonpolar molecule. So just comparing these two in terms of the difference, again, thinking about the tug of war, essentially polar molecules are ones that have an area where someone's winning. There's an overall pull in a direction where you're like, oh yeah, the electrons are definitely going there. This last example, if you look at it, again, carbon and oxygen, very polar. And carbon is pulling a little from hydrogen, but those are considered nonpolar. But again, if we think about this and think about a tug of war, and if someone would win, oxygen is pulling way strong up, and there are electrons then pooling up at the top. So we would say this is a polar molecule. So there's some things labeled for you now on the screen. Again, you have a dipole moment arrow. It's pointing toward the more electronegative with the less electronegative kind of on that plus sign. And I like to think of it as a plus because then I'm pulling or pushing or pointing toward the negative with the plus sign on the positive sign. And then again, that partial charge is because it's polar, right? Not full separation of electrons, but partial positive, partial negative. And then because of how the dipole moments are pulling because of the electronegativity difference, you can see the areas of negativity and positivity. Now, we can do this for all of our atoms, and we're gonna practice this, and I expect you to be able to do it, but there are some things that can help you just right off the bat know whether a molecule is polar or not. Based on molecular geometry, a lot of the times we can figure this out. So because you have to have something that wins, we often say things that are not symmetrical will be polar, because that area of difference in the geometry, that asymmetry, will be probably a place where it's pooling. So a linear molecule is generally considered nonpolar because whether you're pulling like this or like this, those are going to all totally cancel. The only reason it would become polar is if it's not symmetrical anymore. If I had 3 atoms that were all different, it could become polar because one could overwhelm the other with its pull. Bent things are always polar because they're already not symmetrical, which means whether you're pulling like this or pulling like this, there will be an overall pull. Planar things are generally considered nonpolar because they're totally symmetrical. As I pull like this, this, and this, all 3 of those cancel. And you can draw the results, the vectors adding if you want to verify that. Trigonal planar can become polar, though, if you have an area of difference. And that was the formaldehyde example from the last slide. That was trigonal planar, but because I had O up top and H is on the bottom, there's no overall pull. Trigonal pyramidal will always be polar. That is not symmetrical. I have an area of difference smack dab at the top. And then tetrahedrals tend to be nonpolar, totally symmetrical, 4 bonds canceling each other out unless there is an area of difference, right? Something there that makes it polar because I have one that's different than the rest, in which case there could be an overall pull. So the general rules to help, similar to what I just said, nonpolar means that they're symmetrical, or they all have nonpolar bonds that aren't able to pull anyway. Pyramidal and bent are always polar, even if their bonds are nonpolar. Because of the lone pairs, they will not be symmetrical in terms of their electrons. For tetrahedral and trigonal planar and linear, those are all symmetrical, so they tend to skew to nonpolar unless there's an area of difference, in which case they would become polar. So there's the general overview of how to determine if a molecule is polar. Have a nice night.